Hey everybody, Jake here coming at you with another live math lesson this week. Going to be doing a little bit of concavity, inflection points, and second derivatives today. This is something that I've kind of talked about briefly in some of my recent videos, and I wanted to take a little bit of a deeper dive, specifically focusing on concavity, inflection points, and second derivatives. Because in my previous videos where I talked about these topics, it was kind of along with some other topics. So I wanted to just kind of, focus on these specific things a little bit more, because all three of these things are going to be very closely related to each other, and much as a result of that, much more closely tied to the second derivative of a function instead of the first derivative, like some of the other topics that we've talked about recently on my channel. So we're going to be getting into those things today. As always with these live streams, coming at you Monday night, 5 o'clock Pacific time, 8 o'clock Eastern. If you have any questions on anything we're going over, or any off-topic questions even, feel free to throw them in the live chat. I'm happy to help address any questions you may have as we go through this problem, whether it's about the problem, the topic, or some other completely different problem that you've been kind of stuck on. So throw any questions in the live chat. I'll do my best to help you out. But without further ado, let's go ahead and jump into the topic here. And we will talk a bit about second derivatives, concavity, and inflection points. So here's how the example that we're going to be going over to kind of discuss these things. We're going to find the intervals of concavity, inflection points, and the second derivative of this function here, h of x equals x to the fifth minus 2x cubed plus x. So when you're doing a problem like this, trying to find these three things, the first step is basically going to be to find the second derivative of your function. And the reason for that is the second derivative is necessary to start with, because we have to use it in order to find the intervals of concavity and the inflection points. So even though the problem kind of lists them in a different order, we do want to start with the second derivative. So what is a second derivative? How do you find the second derivative of a function? Well, a second derivative is essentially just the derivative of the derivative. So in other words, if we're trying to find the second derivative, we would want to say we have the derivative of our function, and then we would take the derivative of that, which basically is the same as saying h double prime of x is the second derivative. So this is what we're looking for. Well, how do you actually find that? You're just going to take the first derivative and then take the derivative of the first derivative. So first thing we need to do is find the first derivative. We're just going to take the derivative of this function. In this case, we have a polynomial. A polynomial can be, you can find the derivative of a polynomial just by using the power rule. So the power rule says we're going to take our power, bring it down in front. We're basically just going to take this one term at a time. So we're going to take the 5, put it down in front, leave our base x as x, and then minus 1 from the power. 4 minus 1, or 5 minus 1 is 4. So 4 is going to be our new power. So we're going to get 5x to the fourth. And then same thing here. We're going to do the power rule. So we're going to take our 3, move it down in front, and multiply it by whatever our coefficient is. In this case, -2. -2 times 3 is 6, or -6. So we're going to get minus 6x to the 3 minus 1 is 2. And then the derivative of x is just 1, so we're going to get a plus 1. So this is our first derivative. Now, like I said, to find the second derivative of a function, you just take the derivative of the derivative. So we're going to find the derivative now of this function right here, and that is going to give us our second derivative. If that makes sense so far, before we kind of go on to this step here, do me a favor and drop a comment. Just say I got it so far, so I know you're getting it so far. And if you are getting value out of this video, go hit that like button. All right, so to take the derivative of this function, again, we can just use the power rule for this first term here. So we'll move our 4 down in front and multiply it by our coefficient. So 5 times 4 is 20. Leave our x as x, and then minus 1 from the power, giving us 20x cubed. To find the derivative of this term, we can again just use the power rule. So we bring our 2 down in front. -6 times 2 is -12. Leave our x as x, and then minus 1 from the power. 2 minus 1 is 1. anything to the first power is just itself. So that just leaves us with 12x. And then the derivative of a constant is 0. So basically we would have a plus 0 out here. Plus 0 does not actually change the function, so I'm not even going to write that there. So here's our second derivative. The second derivative of this function is 20x cubed minus 12x. Okay, so now what we're going to do is we're going to use that second derivative to find the intervals of concavity and the inflection points. So before we kind of get into that, there is one thing I want to kind of point out, which is a little bit odd when it comes to inflection points and what the definition of an inflection point is. So essentially, inflection points, I've seen them kind of defined a couple different ways. They all basically get at the same thing though, which is an inflection point occurs when you have some spot on your function where it switches from being concave up to concave down. So like basically right here, it's concave up. Right here, it switches to concave down. So in other words, it's curving upwards and it switches to curving downwards, or vice versa, right? If you're concave down and then you switch to concave up, that point where you switch concavity, that would be an inflection point. Now, this kind of relies on the function actually being continuous around that point. So what I mean by that is, let's say we have like a vertical asymptote of a function, okay? And we are concave up to the left of it, creating this vertical asymptote, and then we're concave down to the right of it, creating a vertical asymptote. This x value right here wouldn't really be an inflection point though. And it's kind of weird. It basically switches from concave up to concave down, but there's not actually a point on our function at this spot. So basically what we need in order for something to technically be considered an inflection point is we need our original function to actually exist there. So really we're looking for inflection points specifically within the domain of our original function. Now, in this case, this function here is not going to have a vertical asymptote. And in fact, looking at it, what we have is a polynomial. So polynomials have a domain of all real numbers. So this original function, h of x, has a domain of all real numbers. That's what this symbol means here, just all real numbers. What that means is it's continuous everywhere. In other words, any possible x value is within the domain of our function. So there's not going to be a situation where we are like switching from concave up to down or vice versa, but not having an inflection point within this example. Now, the reason why I say this is kind of a weird topic is even though there technically wouldn't be an inflection point on this function right here at this vertical asymptote, you still would want to kind of consider that as an edge or basically an edge of your interval if you're looking for intervals of concavity. So that's why it's weird. We want to kind of treat it as if it's an inflection point and use it like an inflection point as we look for intervals of concavity. But technically it's not an inflection point because we need, inflection points are just going to be points that are within the domain of your original function. So keep that in mind as we kind of continue our discussion of these things here. I'm not going to consider, well, like I said, in this case, our function, its domain is all real numbers. So it's not really going to come up here. But if you're doing other similar examples, you want to keep that in mind because you would want to kind of use spots like that. And I'll get into what exactly that actually looks like here in a second. But you're going to want to use that for the intervals of concavity, but you're not going to want to consider those inflection points technically. So let's get into how to actually find those things with this example. So intervals of concavity and inflection points. Typically, these things are they're tied very closely together, obviously. I like to kind of start with the inflection points, and I'll kind of talk about why in just a second. But basically, the first step in finding inflection points and intervals of concavity is going to be to take your second derivative and set it equal to 0. So basically, we're just going to take this function right here, 20x cubed minus 12x, because that's our second derivative of our function, and we're going to set it equal to 0. And then from there, we're going to solve for x. Okay. So how would we solve a function like this for x? Well, what we can do is whenever you have some sort of equation equaling 0 and you're trying to solve for x, typically a good strategy is to see if you can factor it. So in other words, look for any sort of term that these two things have in common, the 20x cubed and the minus 12x. What do they have in common? Or in other words, what are they both divisible by? Well, they're both divisible by 4, and they're both divisible by x. Okay, so we can basically factor out a 4x out of the left side of our equation here. So if we factor out a 4x, what will that leave each of these terms with? If we take 4x out of this, we're going to take 4 out. We're going to be left with a 5, because 4 times 5 is 20. And then if we pull an x out of an x cubed, we're going to be left with x squared, because x cubed divided by x is x squared. Okay. And then from minus 12x, if we divide minus 12 by 4, we're left with minus 3. And then if we divide x by x, it doesn't leave us with anything, just a 1. 3 times 1 is just 3. So basically that's what's going to be left. Okay, so whenever you have something factored like this, what you can then do, if you know that you have this kind of factored thing equals 0, what that allows you to do is split this into two separate equations. So we can take each of these parts, each of these factors, and set them equal to 0 by themselves. Because if one of these factors is 0, the product of 0 times anything else is also going to be 0. So we would have 4x equals 0, and 5x squared minus 3 equals 0. Okay, so now we have these two simpler equations which we can solve for x. So in this case, we can divide both sides by 4, just giving us x equals 0. Over here, we can add 3 to both sides. Then we can divide both sides by 5. And then we can take the positive and negative square root of both sides. So you do want to be careful with that. You do need to take the positive and negative square root whenever you have x squared equals something. The square root will cancel with the square root over here, but you always need to take the plus and minus square root of whatever you had on the other side of your equation. Whoops, it's going to be 3/5. There we go. So we're going to have 3 basically potential inflection points. So like I said earlier, technically we don't know that all 3 of these x values are inflection points yet. However, this basically what we have kind of figured out at this point is our possible list of inflection points. So, a lot of times in calculus, these would all just be considered inflection points. And, I really don't think there's going to be that many situations where your professor or your teacher is going to mark you wrong for saying that these are all inflection points necessarily. But you do want to be careful because technically we don't know that they're inflection points yet. To figure that out, what we're going to want is to find the intervals of concavity, which is the next thing we're going to be talking about here. And we need to make sure that to the left of each of these inflection points, we are either concave up or concave down, and then to the right, we are the opposite. So we need to make sure that we're switching from concave up to concave down, or vice versa, at these 3 points. And if that's true, then they would be inflection points. And we do also know that because our original function has a domain of all real numbers. So if our domain was limited in some way, if there were some x values that we could not plug into this function, then you would want to be careful of that as well, because let's say, for example, the domain of our function was all x values greater than 0, and we found x equals 0 as basically a possible inflection point. You wouldn't actually want to use that as an inflection point, because if our function is not defined for x less than 0, it's only defined for x greater than 0, or equal to 0, I should say. It's not going to be an inflection point because we can't switch from concave up to concave down at x equals 0 if we know that our function doesn't even exist for x less than 0. So if that makes sense, leave me a comment, just say, makes sense, I got it. But basically that's the idea there. So obviously, like I said, the domain stuff doesn't really come up in this example, but just to kind of give you a tip for other problems you're going to run into, you want to be careful of that. In this case, let's go ahead and move on to the intervals of concavity, and we can use those to kind of confirm that these are actually inflection points. So once you have taken your second derivative set it equal to 0, solve for x. That gives you your list of possible inflection points. What you want to do then to use those in order to find your intervals of concavity, you're going to take them and you're going to draw them on a number line. So you're just going to label on your number line however many possible inflection points you found. In this case, we got 3. We got negative root of 3/5, 0, and positive root of 3/5. So these are our possible inflection points. So notice what this does if we take our number line of all real numbers and split that up into these sections here, basically splitting it at the points where we have our possible inflection points. What we've done is we've created basically 4 chunks of our number line, right? We've basically split our number line into 4 chunks. We have all the numbers over here, all the numbers between these two, all the numbers between these two, and all the numbers that are basically greater than all of them. So what we basically did is we split all real numbers into 4 different intervals. So what I like to do is just right off the bat, write those intervals out, because those are going to be your possible different intervals of concavity that you want to test for. So we're going to go from negative infinity to negative square root of 3/5. We want to go from negative square root of 3/5 to 0. We want to go from 0 to positive square root of 3/5. And we want to go from square root of 3/5 to infinity. So these are going to be the 4 intervals that we want to test. Well, how do we actually test these? It's pretty simple. All we have to do is go back to our second derivative. So we're going to go back to using this function here. And in fact, what I like to suggest is using the factored out version of your second derivative, because it's actually going to be a little bit easier. So let's go ahead and just kind of copy down our second derivative down here. But we're going to copy down the second, the factored out version. So h double prime is going to equal 4x times 5x squared minus 3. Okay. So once we have found our second derivative, split out our different intervals, what we're going to want to do is we need to figure out for each of these 4 intervals here, is our original function concave up during those intervals or concave down during those intervals? And how we do that is we just take some number that is within each of these intervals. It doesn't really matter what number it is, but some number within each of these 4 intervals, and plug it into our second derivative. So let's just say we're going to plug in for this interval, -1 is within this interval. So let's say we plug in -1. Within this interval, the square root of 3/5, let's just say we plug in from 0 to positive square root of 3/5. Let's just say we plug in 0.1. That would be within that interval. Okay. Then if we take some number within this interval, let's just say -0.1 is between negative square root of 3/5 and 0. And then some number over here, we will take +1. So basically, if we plug these 4 numbers into our second derivative, that's going to tell us if our original function is concave up or concave down within each of these intervals. The important thing to keep in mind here, it doesn't actually matter what number we get, right? If we plug in -1 into this function, we don't really care what number we actually get. All that we care about is if it is positive or negative, okay? So that's really all we have to figure out. So looking here, plugging in -1 into this function here, let's think about each of our factors. So if we plug in -1 here, we're going to get 4 times -1. That's a negative number, okay? And then -1 squared is +1, times 5 is +5, minus 3 is +2. So that's a positive number. So if we plug in -1 into this second derivative, we get a negative number times a positive number, which is a negative number, okay? Now again, it doesn't matter specifically what number we get, we just care if it's positive or negative. So let's do it again with 0.1. 0.1 times 4 is positive. 0.1 squared is going to be 0.01. 0.01 times 5 is 0.05. 0.05 minus 3 is going to be negative. Okay, so we're going to get a negative times a positive is a negative. So we know that we're concave down within the interval that 0.1 came from, which is this one. Okay, then we'll plug in negative 0.1. I'll go a little quicker now. 4 times negative 0.1 is a negative number. Negative 0.1 squared is positive 0.01 times 5 is 0.05 minus 3 is negative. So we get a negative times a negative is a positive. And then if we plug in positive 1, we get a positive here and a positive here. A positive times a positive is a positive. So basically for each interval that these correspond to, so for h prime of negative 1, that came from this interval right here, we know that our second derivative is negative. Since the second derivative of a function tells us about the concavity of the original function, if the second derivative is negative within this interval, then the original function is concave down. Okay, so our original function is curving downward within this interval over here. Okay, so we can just kind of draw a little downward curved line here, a frowny face shaped line. Okay, then we know that we had our second derivative is negative for 0.1, which was in this interval right here. If it is the second derivative is negative, that means the original function is concave down. So this is curving downward. That was this interval right here from 0 to √3/5. Okay, and then these other two intervals, which came from these two, or these other two second derivative outputs were positive. Those came from these two intervals here and here, which means these are both concave up, which means our original function between negative √3/5 and 0, negative √3/5 and 0, this is concave up. And then for x's greater than √3/5, it's concave up also. So basically our original function we know now is concave down over this interval, negative infinity to negative √3/5, concave up from negative √3/5 to 0, concave down from 0 to positive square root of 3/5, and concave up from positive square root of 3/5 to infinity. So basically we kind of have this, it switches its concavity a few times, but what that also confirms is that all three of these points here are in fact inflection points, because you can see that our function switches from concave down to concave up, from concave up to concave down, and from concave down to concave up at those 3 points. So we know that those three are all inflection points in this case. These two right here and x equals 0 up here. So that's really all there is to that problem. I'm not seeing any questions in the live chat. If you do have any questions, if you're watching this later, just throw it in the comments. And if you did get some value out of this video, do me a favor and hit that like button. It's a huge help to my channel so I can keep making more videos like this. And if you did get some value out of this video, be sure to hit that subscribe button too. If you like good grades in calculus, I'm going to have much more helpful videos coming out. So subscribing will make sure that you get to see all those and keep your grades up in calc. So let's keep crushing it all term long together. And I'll be along for the ride with you. But that's all I had for you today. So hope to see you next time for my my live streams each Monday night at 5 o'clock Pacific time. I'll be back next week. See you then.